I am very happy to introduce my friend and collaborator, Sandro Radovanović. Sandro works at the Faculty of Organizational Sciences of the University of Belgrade. He studied informatics and he just defended his PhD thesis. He publishes in the field of algorithmic decision-making, more specifically machine learning, data mining, and decision support systems. Today, he will talk about affirmative actions in algorithmic decision-making. Welcome.
Thank you, Vlast, for the introduction. It is really a pleasure talking here today. Well, as Vlast said, I just defended my PhD, so I'm pretty excited about everything. And the title of the talk is the effects of affirmative actions in algorithmic decision-making. And just to give a brief introduction about myself, I finished computer science at the University of Belgrade. And the field about social sciences, philosophy, and legal frameworks is a bit out of scope of my work. So I've just read several books or papers about affirmative actions, and my knowledge about those topics could be a bit flawed, but hopefully I got it right based on the reading and my understanding of the field. So. Just to give a brief introduction about what have been done by myself and my co-workers about affirmative actions in algorithmic decision making, I will give a brief motivation. So in today's business, both in private and public sector, algorithms are being increasingly used for automatization of the decision making, and there is a reason why is that. So time to decision is shorter. Algorithms are able to process information and data much faster than the human expert, and they can derive a decision very instant when it is needed. Also, the cost of making a decision is much lower compared to the human expert. We don't need to hire a human expert to process data and provide a decision. That can be done by a computer, by an algorithm, and the cost of hosting a server or something like that is really low. And the best of all, algorithms have performed better compared to the human decision makers. And a lot of both public and private companies bought the idea of algorithmic decision making. Everything is better compared to the human expert. And for a very long period of time, it was believed that algorithms can only help. And not in the sense only in the shorter time period to make a decision in a lower cost and better accuracy, but it was a belief that algorithms are bias-free. So they create only just and fair decisions. Therefore, the injustices and biases of the human decision expert will be removed just by using an algorithm. And if we talk about algorithms used for automatization of this decision making, they are solving mathematical problems or mathematical models. And those mathematical models most often look like minimization of a loss function. And sometimes we have some constraints about the model, mathematical model. And since if I understood well, most of the audience is from the field of philosophy, just to give a brief explanation, how does it work? So we have some data set, some historical data, where row of the data sets are subject for which we are making some decision, and columns of the data sets are attributes which give context and describe each subject for the decision making. And this part of the table denoted in blue is input attributes denoted here in X. And most often, and in the field of algorithmic decision making, when we want to mimic decision maker, we have an additional column, an additional attribute, which says the real state of the subject in the some future. And it is denoted with Y, and it's also here Y. And we are trying to find the patterns and relations or associations between attributes and this Y attribute or label attribute. And one common goal function is logistic loss, where we compare true value with the prediction value. So we want those two to be as close as possible. And in order to create a decision-making model based on an algorithm, we must use historical data. And just to give two simple examples. Imagine we want to hire someone, and we want to use data from previous hiring to make to automate decision making. So if a human decision maker said, for example, I will hire male candidates because they work better, algorithm that uses that data will most probably inherit that bias in human decision expert. Another example, student enrollment data. For example, in STEM fields, where if we want to contact students, possible students in STEM areas, male participants, male candidates for enrollment are more probably more likely to be reached because they are more enrolled in STEM areas. Therefore, if we have a bias in historical data, algorithmic decision making will inherit that bias, but not only inherit that bias. Most likely it's going to amplify bias and create a bigger problem. And the biggest problem of all is that we are not aware where is the source of that unfairness and how can we identify it. In the first example, it was a human decision expert bias. In the second example, it was cultural or historical bias. But the bias can originate from data collection process or sampling bias. So bias can exist if we are blind to some area and we are not collecting data from that field. And from 2015 onwards, people started questioning algorithms. And there is an example of robot recruiting, where hiring could become faster and less expensive and lead recruiters to more highly skilled people who are better matches for their companies. And there was a promise that this algorithm is free of human biases. And a lot of companies bought that promise. But the algorithm used in information, so it tried to predict whether an employee will be a good employee, whether that employee is going to be hired or not, and what is going to be about the fluctuation of those employees. And one part of the predicting task that was used was based on a was based whether an employee is going to work several years without sick leaves. And of course, algorithm started predicting male candidates more often than female participants. Therefore, software was not free of human influence, and not only it replicated but reinforced human prejudices that existed in data. There are another examples. Example like ProPublica Compass, where two employees of some company was late to work and stole a kid's bike and a scooter. It was mid-30s white Caucasian male person, an 18-year-old African American female. And because of petty theft, both of them performed a petty theft. She was declared as high risk of reoffending, and therefore she was sent to jail sentence. And he was deemed as low risk, and he was not sent to jail, he was sent to probation. And after observing what happened and what is happening, it is found that an algorithm is likely to falsely flag black defendants as criminals and wrongly labeling them almost twice as rate as white defendants, while white defendants were mislabeled as low risk more often than black defendants. So it was a pretty social unrest situation here that really replicated in the real application of such predictive model or algorithmic decision making. And even great companies, big companies like Google are not well. They even have problems with unfair decisions and biases. So just by changing gender in ads in a setting, male participants will get ads for higher paid jobs compared to the female participants. And so making biases and making injustices in algorithmic decision making is something that is pretty new. And we would like somehow to regulate that. So we don't want to just replicate the real situation. We would like to help underprivileged groups. And the biases that we don't want to create are somewhat regulated. So we cannot create discrimination based on education. We don't want to make discrimination in employment. And more recently, there are some legal documents that regulate algorithmic decision making and biases and affirmative actions in algorithmic decision making. But what are the properties for which we want to create an affirmative action? Well, those are mostly defined by Civil Rights Act, and those are race, sex, age, or religion. But there are others, but those four are mostly used, and they are even they can be found in GDPR as well. But in order to improve or in order to assign and get an affirmative action in decision making, algorithmic decision making, we must be able to somehow measure bias in the data or bias in the decision. And there are several measures that can be used, and most of them are derived from Civil Rights Act. And the first one is disparate treatment. Disparate treatment says that an individual or group of individuals are getting the lower expected score, a lower score, based on the personal characteristics such as race, gender, etc. And they are getting that score intentionally. And since those errors are subject to legal consequences, we are going to say that we don't expect those kinds of biases in the data. The biases in the data can be a result of a culture or historical disadvantage of some certain subpopulation of the group, and therefore we are going to use disparate impact. So these algorithmic decisions can create disparate impact. Direct mathematical formulation from Civil Rights Act is presented here. So it is expected probability score or expected score to get the desired outcome. Well, more specifically, expected probability to get the desired outcome should be independent of the group belongingness. So group belongingness is denoted with S, and the Y hat is expected or probability of getting the desired outcome. So expectation to get the desired outcome, given the belongingness to the discriminated group, S equal to 1, should be exactly the same as the expected outcome of belonging to the privileged group, S equals to 0. So we want this ratio to be as close as possible to 1. And if we assume that privileged group is having a higher expected probability for getting the desired outcome, this ratio is always going to be lower than 1. So we are wanting to hit the ceiling or hit the max to have exactly score 1. And this is not the only measure used in algorithmic decision making or fairness in algorithmic decision making. One measure that is also commonly used is called equalized odds, that says that expected probability score for getting the desired outcome should not be independent on belongingness to a group, such as race, gender, etc., but also for every possible outcome that exists in the data. So not just by just getting the desired outcome, but other outcomes as well, not desired outcome and other outcomes as well. And in the field of algorithmic decision making, we are trying to correct biases or mitigate biases. And if we compare bias mitigation with affirmative actions in the legal field, it's pretty much exactly the same. It really looks one to another. Well, affirmative action is seen as a legal mechanism that is aimed to equalize resource allocation by giving more opportunity to disadvantaged group or discriminated group. So we are going to we are going to give the discriminated group additional amount of resources in order to correct historical or cultural biases. In the field of machine learning or algorithmic decision making, we have different mitigation strategies that are aimed to reduce disparate impact in the decision of a decision-making model or algorithmic decision-making model. So if we observe in the data using disparate impact previously mentioned and see that there exists disparate impact, we somehow mitigate that disparate impact and in our decisions made by algorithmic decision-making, reduce that disparate impact, that is probably some way to implement some affirmative action. And in several papers and several books, it is said that this is a type of affirmative action. But whether is that a true affirmative action or not? Well, there are some differences. Fairness mitigation strategies are more broad than affirmative action defined in a legal theory. So an affirmative action tries to help every individual belonging to some group, for example, females. We are going to help every female get some resource. We are going to help every African American get some resource. But in the field of machine learning, we are not going to help everybody. We can observe not only the part of the group. Well, I'm sorry, we are not going to observe the whole subpopulation. We can observe part of the group. Female African Americans, we are going to help just them. We are going to help not only them, but just those subjects that are going to get or close to getting the desired outcome. So there are some differences, but mostly it is seen, fairness mitigation strategies are seen as an affirmative action. And what are the strategies that exist in the algorithmic decision making? The first strategy is fairness through unawareness. So if algorithm is unaware of sensitive attributes, it is called sensitive attributes. So if an algorithm is unaware of gender, race, or religion, it should provide fair decisions, and thus it will improve the situation of the discriminated people. So if we have an additional attribute S that denotes sensitive attributes, we are going to create a model that will not look at that attribute at all. However, this did not result in the greatest improvement in fairness and affirmative actions per se, because other attributes that are used for decision making can be a proxy to a sensitive attribute. For example, place of residence can explain race of an individual. Therefore, people tried, okay, let's remove correlated attributes with the sensitive attributes. But we are losing a lot of information and therefore prediction performance. So we are not going to make good predictions about the problem at hand, although fairness is improved. So the only strategy to improve fairness and provide a true affirmative action is to be aware of the sensitive attributes. So we have three approaches. One approach is to prepare data prior to learning a prediction model. So we can adjust data to be more fair. And if we have an original data set, we can say, okay, let's add a weight to each individual. And we are not going to make a mistake on sensitive population. We want to give them higher weight. So algorithm will say, okay, these instances are very important. I'm not going to make a mistake on them. And this approach is called reweighting, and it is helpful for reaching fair decision making. Another approach, just to mention another approach, it is massaging. It's called label massaging. So instances or subjects belonging to the discriminated group are falsely going to be set to get the desired outcome, even if they didn't receive the desired outcome. while the instances of the privileged group are going to be set to not get the desired outcome, even if they got the desired outcome. And that is performed at random with a very small percentage of an example. And this really improves fairness. However, data preprocessing have a major flaw. With new with new legal documents such as GDPR, there is a need for that data accuracy. And if we change data such as this, we are not using accurate data. And we can be a subject of legal consequences just because of that. Therefore, people try to solve problem differently. So if we are not going to prepare data to be fair, can we intervene during the model learning phase? So if we intervene in the algorithm itself, can we make better decisions? Can we promote equality in the decision? And those are called in-processing techniques. And several approaches exist. So we can do a constraint optimization. So we are going to learn the best possible prediction model with fairness constraint. So we are going to create a model that will satisfy some level of fairness. So we are going to promote underrepresented and discriminated group by giving them greater opportunity to reach the desired outcome at some certain level that is guaranteed. However, more frequently, people change a hard constraint and put it in the goal function, and this is called the regularization functions. So we are going to learn the best predictive model, and complexity of the model is going to be controlled by the fairness. So we are going to create injustices only if they are explaining predictions much greater. And we can use adversarial learning. This is a kind of novel thing, relatively novel, from 2018, where we are at the same time learning a model which will be most accurate and most fair. And most often people use in-processing techniques, at least in machine learning. However, we have an additional mitigation strategy, which is called post-processing techniques. So once the model is learned, we are adjusting the results of the model to get a fair prediction and promote equality. So just a brief example, we have a true label here, true outcome, where 1 present desired outcome, 0 present undesired outcome. And y hat is the prediction or probability of getting the desired outcome got by the prediction model. And we need to decide what is the threshold for assigning these 0 or 1 based on the probability. So we are going to put some threshold, and every probability greater than that threshold is going to be assigned 1, and lower is going to be assigned 0. And if we observe this threshold, we have the best possible classifier. We have the best possible algorithmic decision-making model. It is going to be 100% accurate. So if we assign ones here, they are going to be exactly the same as ones here. And zeros here is going to be exactly the same as here. But if we observe sensitive attribute, 2/3 of the privileged group, so those the instances where S is equals to 0, are going to get the desired outcome, while 1/3 of the discriminated group is going to get the desired outcome, this one. And post-processing techniques would most probably put another decision threshold, for example, here, and we are going to lower our precision, lower our accuracy of the model, and it is going to be here 5 out of 6, that's 83%. And only one instance of the privileged group is going to get the desired outcome. And by just adjusting the decision threshold, we created fair prediction model. But this is not an affirmative action, so we just made it fair. So we are not making disparities in this decision. Okay, and what we wanted to do in our first paper, we wanted to promote equality in algorithmic decision making. So create some kind of affirmative action to discriminated group and promote to get the perfect value of the disparate impact. So the disparate impact is defined as a ratio of expected probability score for the discriminated group and the expected probability score for the privileged group. And this should be higher or equal to some value C. And using that's the lower bound of the disparate impact. And in legal documents, there is no formal guideline, but in the US equal employment right, they say 4 out of 5 people should be white or black, something like that. So 4 out of 5, we cannot create a disparate impact greater than 80%. And from mathematical point of view, expected probability score or ratio of expected probability score is not suitable for optimization. It is a ratio of something that we are trying to learn, and it's not easy for optimization. So we are going to present it in a different manner. So we are going to present a linear formulation of a disparate impact. So we are putting this lower side to the right side of the equation, and we can present it in a linear form. And this is in the field of machine learning called statistical parity. And expected probability score is average probability score. So we can present it as this. And the next problem is using probability score. It's also not suitable for an optimization. And instead of using probability, we are going to use prediction intensity. So that is a number prior to a sigmoid function that transforms this value into a probability. And this is a linear formulation of a disparate impact that can be optimized in the mathematical model. And in our paper, or our approach, used just a modification of the disparate impact, saying that instead of 2 sums, we can put it in a 1 sum. And to recall, S is a sensitive attribute, where 1 belongs to represent the instance or subject belonging to a discriminated group, and S bar represents average number of people belonging to discriminated group. So if a person belongs to a discriminated group, this part in the this part here is going to be positive. So we are creating a positive discrimination. So we are multiplying that with the intensity, and this is a positive discrimination. If an instance belongs to a privileged group, this value will be negative, multiplying with the intensity score, and this is going to lower down the function value. So this is going to be a negative discrimination. And we want this number to be some value, C. And if we put value C equal to 0, we should get perfect disparate impact. And what this means, what is going to happen? So if we presented this graphically, on the horizontal axis, we have a true outcome where 1 presents desired outcome and 0 undesired outcome. And on the vertical axis, we have our prediction values. We are going to see that privileged group is privileged. They are having a greater expected probability score or average probability score, both for the desired outcome and undesired outcome. And the constraint that is implemented, that is explained previously, increase overall probability score for the discriminated group, but in such a manner that expected probability score of the privileged group for not getting the desired outcome is lowered much in much higher intensity. Therefore, on the average, those intensities are same. So disparate impact is perfect, but we can observe that for getting the desired outcome, it is still that the privileged group is more likely to get the desired outcome. And the thing that we wanted is to equalize that here and here. So we want to get disparate impact, but also equal loads. And in this manner, we will act as a true affirmative action. So instances or subjects belonging to the discriminated group are going to be put higher in the ranking and get the desired outcome from the algorithmic decision-making tool. And to do that, we added an additional term here regarding the true outcome value. So not only we are going to optimize for the disparate impact, but this function here is also to optimize for to constrain for getting the equal odds. So we are going to learn practically similar model, thus we are going to optimize for the equal odds as well. And to test our approach, we performed an experiment on the adult dataset, which is a binary classification dataset, which means that we are trying to predict whether an individual is going to get the desired outcome or not, where the desired outcome is census level. The person is receiving a yearly salary greater than $50,000. And we tested different types of logistic regression. So we used the plain logistic regression, lasso logistic regression, the regional logistic regression, logistic regression that optimized just for disparate impact, and our proposed logistic regression. As a measure of performance, we used area under the curve. It is a binary classification metric which is independent of the decision threshold. That is the reason why we selected this measure. And this measure is have values between 0 and 1, and more specifically between 0, 5 and 1, and higher value is better. And as a measure of fairness, we measure disparate impact and equalized odds as well. More specifically, disparate impact for one outcome, desired outcome, and disparate impact for undesired outcome. And this is a bit technical note here. We perform tenfold cross-validation. Therefore, we are training the model on one data set and testing on the another. More specifically, the whole data set is split on 10 parts, and we used 9 parts to learn model and the remaining part to test the model. And we performed that 10 times such that each subset of data is used exactly once for testing. And we used inner tenfold cross-validation for parameter optimization, hyperparameter optimization that exists in the lasso and ridge logistic regression. And these are the results. So here, the first column is AUC, or which is predictive performance. And we can observe that fairness unaware logistic regression have a higher area under the curve compared to the logistic regressions that were aware of the fairness issue. So, and it is not a small price to pay for fairness. It is almost 10% reduction in the AUC, which is really a great cost in accuracy. But if we observe the data set, we can see that the data set was initially very, very discriminated. The value of disparate impact 0.39 means that the male participants had more than twice higher probability compared to female participants to get the desired outcome. So it was very unfair, but our constraints, or to be more fair, the constraints presented by Zafar and his team, and our modification of that constraint managed to achieve very fair results. So the disparate impact is almost a 1. So this means that both males and females in the results of the decision, in the result of the predictive model, have on average same expected value to get the desired outcome. And the only thing that disparate impact logistic regression did not solve is equal odds. So disparate impact for, or let's say expected probability score for not getting the desired outcome was higher for female individuals. So they are not going to get the desired outcome, but they are ranked higher. And this was a bit misleading. So they are increasing disparate impact, they are increasing the score, but this is not the true affirmative action as defined in the legal documents. our approach did better in this field. So it improved both disparate impact and expected probability scores, both for getting the desired outcome and not getting the desired outcome. And just to have a brief discussion and to mention something that is in the title of the talk, effects of the affirmative action. So what are the effects of getting the intervention to get a more equal representation of groups in the data? So the measures that we are using in machine learning or computer science to measure bias and unfairness are improved and can be improved in decision-making process. Therefore, in some sense, we can enforce equality in decision-making. But what are the costs? The costs are in predictive performance. So if we are going to make more equal decisions and promote equality, we are going to pay that price in predictive performance. So if we are assigning some resources, we are going to lose some resources because of that assignment. And whether this is a true affirmative action, if we are intervening, if we are providing an intervention in the algorithmic decision making by putting a hard constraint in the mathematical model, are we performing a true affirmative action? Well, no. What can happen is that after performing an intervention, we are making average probability score per group exactly the same or close to the same. And that result in several consequences. First, we are most likely to decrease the probability score for the privileged instances, for the privileged subjects. And this is not something that is desired property. So if somebody is deserved to get high probability, well, it should get a higher probability for getting the desired outcome. We should not reduce their probability for getting the desired outcome just because we want to achieve similar or same disparate impact. On the other side, we are increasing the probability score for the discriminated instances, and that is a good thing. We want to increase those probabilities. But what is the problem both in this, and both for privilege, decrease in privilege, for privilege and increase for discriminated, is that that is happening on average. So it can happen that somebody is decreased its probability for a large amount, while somebody is going to have a decrease just for a small amount. Or for discriminated group, some instances in the discriminated group are going to have a much higher increase compared to the other. And it can even happen that some instances are going to have a lower probability score than before the intervention. Therefore, within group order or ranking within group is changed. And this is something that is not desired in the affirmative action. If we are helping a discriminated group, we are going to help them each and every one the equal amount. And therefore, Vlasta and I try to create an affirmative action in algorithmic decision making or a machine learning model. And this is something that is currently submitted to bias and algorithmic decision making workshop. So this is so in order to get a true affirmative action, we are not going to intervene in the data. We are not going to intervene in the decision making model because it is hard to intervene to provide a true affirmative action in the machine learning model. We are proposed post-processing technique. This means that whatever algorithmic decision model we have, they will produce the probability of getting the desired outcome, and we are going to intervene on those probabilities. And we are going to intervene in such a manner that we are going to add an additional probability for getting the desired outcome only for those instances that belongs to the discriminated group. And the problem we try to solve is to find that parameter alpha. But that is the amount, that is the probability that is going to be appended or added to the discriminated group in order to achieve fairness, in order to promote equality and in the real world. And we had one simple problem: how to measure disparate impact. So we have the one that is used previously. We called it probabilistic disparate impact. It is a ratio of expected value of getting the desired outcome, having the belongingness to the discriminated or privileged group. But since we are intervening in the decision-making process, so we are not interested in the probability scores, but in the decision itself. Therefore, we want to have the same expected value of getting the desired outcome, or probability of getting the desired outcome, but by setting the desired outcome to the individual. So this is called decision disparate impact. And how are we going to decide what is parameter alpha for this one and what is the parameter alpha for this one? For this one, for probabilistic, it is pretty easy to derive alpha, and it is going to be calculated as this. So this is a desired level of the disparate impact, multiplied by the expected probability score of getting the desired outcome for the privileged group, reduced by expected probability score for getting the desired outcome for the privileged group. And for the decision disparate impact, that is a bit more problematic. It is not a nice mathematical formula, nice in mathematical sense. And the only way is either to approximate this function, or to use grid search. And we decided to use grid search. So we are trying different values of alpha and selecting the one that is getting the best disparate impact. And the experiment is performed also on the DAO dataset in the similar manner as the previous one. So we measured as a predictive performance area under the curve, AUC, and as a measure of fairness, we only use disparate impact. So we want to have promote equality just by that. And since we are using decision disparate impact as well, it is pretty much similar as equal odds, just to use that. And since there is a different decision threshold, since we are creating a decision, we can use different decision thresholds, and we selected 4 values for decision threshold. The default one, 0.5, which means that if your probability for getting the desired outcome is higher than not getting the desired outcome, you should get the desired outcome. And other that are more used in the private sector, we are going to select top 50% of the instances based on their probability score, top 25 and top 10%, and get them the desired outcome we want. And the other parameter that we tried to change was the wanted level of the disparate impact. So perhaps we don't want to achieve perfect disparate impact. Perhaps that would be an overstatement or overreaching in the sense of equality. That value might be overwhelming for discriminated instances to use this kind of model. So we tested with levels 0.7, 0.8, 0.9, and 1. And if we observe the predictive performance, we can see that this type of post-processing is pretty good. So the loss of predictive performance in terms of AUC is much lower. Well, the difference between the best performing and the one that are not presented in bold letters is lower compared to the previous example. So if we are intervening in the algorithm, we are going to lose more predictive performance compared to the post-processing technique in this manner. And these differences is only by 2%, so it's not by 10%. So it's pretty good. And if we observe the disparate impact that we got, we can see that, okay, using the plain logistic regression, we are going to have a highly biased classifier, highly biased algorithmic decision-making model. And if we are using probabilistic disparate impact, and we optimize for probabilistic disparate impact, we can see that probabilistic disparate impact is satisfying exactly the level of disparate impact we wanted. And if we use decision disparate impact by trying to find the best value of disparate impact to satisfy the desired level of disparate impact, we are not going to get the wanted level. So most often it's going to be a much lower value. So we are going to make a discrimination, and not only we are going to make discrimination, sometimes we are even going to increase and amplify bias that exists in the data, such as here or here or here or here. So we can even amplify bias if we don't choose correct form of disparate impact. And if we are optimizing for decision disparate impact, we can see that, of course, the best performing one is decision disparate impact, and we are satisfying the desired level of disparate impact most of the time. And using probabilistic disparate impact to optimize for the decision disparate impact results in overwhelming affirmative action for discriminated group. So after performing probabilistic disparate impact for the decision disparate impact and measuring decision disparate impact, the discriminated group is having a higher expected probability for getting the desired outcome, or to be more precise, they are getting more the desired outcome than the privileged group. And this level is not small. In some cases, it is over 60%. So just by trying to intervene, we can overcompensate. And just to provide open questions, so there are a lot of open questions: how to intervene, how to perform an affirmative action in algorithmic decision making, and there are some open questions. And the one that is mostly questioned in the literature is if we are intervening in the algorithms, what is going to happen in the long term? So if we are provide some intervention in this step today, whether we are going to improve, whether the discriminated group is going to have a greater probability for getting the desired outcome in a month, in a year, or in the near future, and whether we are going to create an opposite problem, that the discriminated group is going to behave in such a manner that they know that they are going to get an affirmative action, and they were going to stop to try to get a better outcome and improve their situation. And the other question is, what is the level of affirmative action? So in the proposal by Vlasta and I, we are putting different level of disparate impact, but this is a mostly technical issue. But from sociological and psychological level, what is the level? What is the amount of the affirmative action that will result in envy-free decisions? So what I mean by envy-free, if we are helping this discriminated group, whether will the privileged group be envy of the discriminated group? For example, I can be envy for example, for females, if females are getting the affirmative action, I can be envy for not being a female, because if I'm a female, I would get the desired outcome, and I, as a male, even having the same probability, even having the same attributes as a female, I'm not going to get the desired outcome. So this is a question on defining the level of envy-free for affirmative actions. And from a mathematical or computer science point of view, we can create a Pareto frontier or Pareto front. So we can create multiple solutions for our models, algorithmic decision-making models. Let us imagine we have a predictive performance here, and we have a fairness here. we are going to get a whole bunch of solutions like here, and what solution to select. Is it this one here, where the rise of predictive performance, if we are going to rise to have a greater predictive performance, we are going to have a greater decrease in fairness. And if we want a greater fairness, we are going to lose on predictive performance. Or it is some point here, here, or here. So this is a point of, this is a question, what solution to select. And other issues are, since we are using linear approximation of disparate impact, are we going to optimize the disparate impact per se? And in the example that Vlasta and I are trying to solve is using probabilistic disparate impact and decision disparate impact, we saw that disparate impact is hard to optimize. So using approximation such as probabilistic disparate impact is not suitable for decision disparate impact. And another question that is opened recently is, do we want to create fair decisions, or do we want to create affirmative action, or we want to optimize something completely different, such as social welfare? So we are not going to optimize for equity, but overall social welfare. If that requires for discrimination, based on which discrimination, and that discrimination leads to a greater welfare for both privileged and discriminated group, perhaps that is a way to solve the problem. And that would be all. Thank you very much. And if you have any questions, feel free to ask.
Thank you so much. It was great. Any questions? You can just unmute yourself.
Yeah, maybe if I can. I mean, two more conceptual questions, because I mean you make quite clear, let's say, what is, how to say that, the philosophical interest here. But then you use, I mean, quite heavy mathematical stuff, because I mean, artificial intelligence works with that. So can you see that, I mean, you said that you had to modify certain formulas. We don't have to go to the details. And of course, I mean, what for me of interest, or the question goes in that direction, what is the correlation of the qualitative aim you have and the quantitative part in the formulas? To say it differently, let's say, could it be if there is in one denominator a 2 instead of a 3, then everything breaks down, so to speak. So, I mean, how sensible is it to the mathematical details with respect to the overall philosophical or ethical aims the full approach has?
Yeah, thank you. Nice question. And I had a pretty much monologues with myself about similar questions. So if we observe that, just briefly to return here. So is it breaking down? Yes, it is breaking down. So if we choose a different formulation of the measure, and this is the same measure, probabilistic disparate impact and decision disparate impact. It is the same measure, and this one is an approximation of this one. And if we observe the results, it is very sensitive. So we are not getting the desired level of fairness. We are overcompensating here. So we wanted 0.7, we got over 1. So we overcompensated for the discriminated group much higher than the level we wanted. Here we wanted 0.8, it is here. And there is a complete argument, especially, and I will give the presentation so you can check the talks here. In this paper by Maximilian Cassi and Rediet Abebe, what is the thing we want here? Do we want to promote equality? And how are we going to promote equality? So there are mathematical formulations, and since I'm a computer scientist, when I read the formulation in the Civil Rights Act about disparate impact, I pretty much see what is the definition that is presented here. And probably that is not the formula, or probably that was not the idea of the one who wrote that document. And there are a plethora of measures of fairness and equality. And that is also a question that I also like to discuss with Vlasta most of the time. I cannot convince myself that I selected a true measure of fairness. And it's easy to find a counterexample to prove me wrong if I create something. So it can easily break down. Just to briefly answer the question. So I would refer to this paper.
Thanks a lot. I don't know. I mean, I would still have a second question, but I don't know whether there's somebody else wanting to speak first. Let's say the second question was more for the qualitative part at the beginning, where you said, okay, I mean, when we, we want to help minorities, or let's say people which are, how to say that?
Underrepresented,
which get disadvantaged advantages decisions by bias in the procedure. Now, I mean, there was this standard example, of course, at the very beginning, when if you just look for the color, I mean, to take it out alone, that doesn't help because it could be recalculated by the other data and so on. And then, if I remember right, you said, okay, but I mean, somehow we don't just take it out, but we will actively somehow help those which have the supposed to be negative what's Merkmal in English? No, there's characteristics, exactly. So, but my point here is the following. So do you always, I mean, do you have to feed that characteristics? Or is there any way that the artificial intelligence software tells you, I mean, making alarm, telling you, okay, careful. I mean, here I start seeing a characteristic which might result in a bias. And I mean, just to give an example, what I said, I mean, okay, you can have thousands of biased decisions, but what is it if at the end of the day, it's decision against left-handers, but there's no characteristic given. So somehow artificial intelligence has no idea about left and right-handers in the data. So, I mean, it seems to be that it has no chance to find it out by itself if this data is not given. And so here, the analog question, so can your full strategy now, makes this, only work if somehow humans identify the characteristics we want to debias?
Yes, in that sense, only the attributes, sensitive attributes that we provide are going to be debiased in that sense. And to answer the first part of the question, we can have an attributes or characteristics that are biased, and we can observe that. And we can say this attribute is biased and we are not going to use it. And that is the the type of that was used in fairness unaware or fairness through unawareness. But if an attribute has some information about the problem at hand, it's more probably useful to use it than to discard it. And there is an additional hidden problem that in attributes that is called attribute interaction. So there is possibility for a small subspace in the data. For example, if we have, I don't know, geographical location and something education, that only specific combination of geographical location and education level of an individual discover the sensitive attribute. And it is very hard to identify that, because in other combination of those two attributes, it's not biased, but only for that combination, and that combination produces unfair and biased results.
Thanks.
Are there some more questions? I am not seeing anyone, and we are already slightly over time. But maybe I can also just mention if we and kind of ask Sandro to re-mention this kind of how this huge philosophical debate starts with different theories of justice when they enter into a role, and maybe to comment about this problem with egalitarianism and just randomly deciding about who should be chosen for a certain feature.
Okay, well, Vlasta introduced me to theories of justice. It was, well, it was a year ago, maybe something like that. And we had an initial idea to learn models according to the justice theories. And this type of model, where we are trying to minimize the loss function, is seen as a utilitarianism approach. It really seems like that. So we are seeking for the best utility of our model, and we are going to solve for best model. And the more we read, the more I read, I got more confused, and I wasn't really able to lower down the generality of justice theory to a mathematical formulation. For example, I'm not able to lower down in mathematical formulation Rawls' theory of justice. And when we discussed about egalitarianism, it turned out that it is very easily to get perfectly fair models, perfectly fair decisions, but they are not solving the problem. So therefore, using theories of justice solely to provide an affirmative action is probably not a good idea. What would that be? So perfectly egalitarianism approach would say each and every individual should get the same outcome. And in the sense of the prediction models, that means that every individual should get the same probability of getting the desired outcome. And whatever measure of fairness we choose, it will be perfectly fair. But the model itself would not be useful. So that would be pretty much the same as not using any characteristic X, any attribute X, and making decisions, but by not observing any characteristic of an individual. So the most fair decision at that point would be give everybody the same outcome, or decide at random. And Vlasta gave me examples where such models, decision models, are already being used for example, in education for admissions. So perhaps it is not so bad idea. I don't know. I'm not for that. I'm pretty much against that, but okay, it's my opinion.